Recall the example integral x sine x squared dx. This is a product of two different functions. One is a polynomial and one is a trigonometric function. But you might remember how to do this by substitution. Turns out it is very convenient that x is related to the derivative of x squared, which is inside the sine function. And so we can set u to be x squared, which gives us du as 2x dx. Consequently, multiplying inside by 2 and outside by 1/2, we have the integral of 1/2 times sine of u du, which can then be integrated very conveniently as negative cosine u plus c. Going back into x, we have negative half cosine of x squared plus c. But in this example, it was very convenient that x could be written as 2x, which is the derivative of x squared. If you see an example like this though, where x cannot be written as the derivative of what's inside the sine, there's no way to do this by substitution. So this is a product of two different functions, x and sine x, and we cannot use substitution here. This is a good sign that integration by parts must be used. Let's develop the theory for integration by parts. All we need to know is the product rule for differentials. The product rule for differentials says that the differential of the product of two functions is the first function times the differential of the second function plus the second function times the differential of the first function. Now we can integrate both sides of this equation, and if you only consider the left hand side, we have the integral of a differential. Now if you remember, the integral of the differential of a function is just the function itself. And so the integral cancels the differential and you have u times v, and let's keep these integrals as is. So we have integral of u dv plus the integral of v du. Subtracting the integral of v du from both sides, we have uv minus the integral of v du equals the integral of u dv. And just rearranging this formula so that the integral of u dv is written on the left side, we get the famous formula for integration by parts, that the integral of u dv is uv minus the integral of v du. Now it is very important to understand that this formula on the left hand side contains a function u and a differential of another function. And in order to integrate by parts, we need to have both a function as well as a differential at hand. Let's see how we can use integration by parts to integrate x sine x dx. Now we have three choices based on what we set as our function u and what we set as our differential dv. For the first choice, I'll choose the correct choice. I'll set u as x and dv as sine x dx. So that I'm taking u as just the function x and dv as a differential sine x dx. The dx is really important. It's there to show that sine x dx is actually a differential just like dv. So now what? Well, if you have u, we can find du. Since u is x, we know that du over dx is 1, and multiplying both sides by dx, we get du equals dx. Similarly, if we have dv, we can find v by just integrating both sides. Integrating dv, we just get v, and integrating sine x dx, we get negative cosine x. I'm not going to add the constant of integration because for integration by parts, it does not matter. So now that we have u, v, du and dv, we are ready to integrate by parts. The formula again to remind you is integral of u dv is uv minus integral of v du. Applying the formula, we get the integral of x sine x dx equals u times v. Now well, u is x and v is negative cosine x. Multiplying u and v, we get negative x cosine x minus v is negative cosine x and du is simply dx. So we have negative cosine x dx. Simplifying this integral a bit, we have negative x cosine x plus the integral of cosine x dx. Let's take a moment to see what has happened here. We have converted the integral of a product of a polynomial and a trigonometric function into something plus the integral of just a trigonometric function. As you know, this integral is much easier to evaluate than this integral. So we've broken down a complex integral into a simpler integral. Alright, so as you know, the integral of cosine x dx is sine x. We have negative x cosine x plus sine x, and let's not forget plus c. Now you might say, what if I had chosen a different u and a different dv? Well, let's see. For our second choice, let's take u to be sine x and dv to be x dx. So in this case, we have du equals cosine x dx, and v, integrating both sides here, we get v equals x squared over 2. Let's apply the formula now. Integral of u dv is uv minus integral v du, and so the integral of x sine x becomes u times v, which is x squared over 2 times sine x, minus the integral of v times du, which is x squared over 2 times cosine x dx. Now you might notice that the second integral over here is actually more complicated than the first integral. So the second choice of u and dv is failing us. We've not really used integration by parts to simplify the problem, rather we have made it more complicated. And finally, for choice 3, you might say maybe we can take u to be x sine x, and the differential dv can be taken as dx. Well, let's see what happens over here. If u is x sine x, we can see that du will be, using the product rule, sine x plus x cosine x multiplied by dx. And integrating both sides over here, we're just going to get v equals x. You might already notice that our integral is not getting simpler. For instance, if we try to use the formula uv minus integral v du, we're going to get u times v, which is x times x sine x becoming x squared sine x minus, now this one's going to be crazy, integral of x sine x plus x cosine x dx. Of course, you can see that this is a much harder integral than the original question, and yet again, integration by parts has not worked for this choice of u and dv. So of the 3 choices, the only correct choice for u and dv was to choose u to be x and dv to be sine x dx. But why was this choice? Why was the first choice so convenient for us? This is because integration by parts is designed in such a way that the function that you choose gets differentiated while the differential that you choose gets integrated. So in general, it's most efficient to choose a function which, when differentiated, makes your life easier. In this case, differentiating x just gives us 1, and 1 is the most convenient thing ever. Whereas if we had chosen u to be sine x, du would be cosine x. Well, this is not really simplifying. Similarly, in choice 3, if we chose u to be x sine x, now du becomes even more complicated. In general, choose u to be something that, when differentiated, makes your life easy, and dv to be, well, whatever else is remaining in the integral. In a lot of questions, the choice of u and the choice of dv will not be very intuitive, and it is only after practicing lots and lots of examples will you develop a better judgment of what to set as u and what to set as dv. Let's consider a few more examples to improve our judgment. In this case, we have the integral of x squared e to the x dx. Now try to pause the video and think about what you're going to set as u and what you would set as dv. Remember, u should be something that, when differentiated, simplifies the integral. So the correct choice is to choose u to be x squared and dv to be e to the x dx. Again, I'll remind you that it's really important to include the differential in the dv. Since u is x squared, we get du as 2x dx. And since dv is e to the x dx, we just get v is e to the x. Applying the formula, we get the integral of x squared e to the x is u times v, which is x squared e to the x, minus the integral of 2x e to the x dx. Let's integrate by parts once more. This time, since we've already used u, dv, du, and v, let's define new variables. Let's call 2x as u1 and e to the x dx as dv1. So we have u1 equals 2x and dv1 equals e to the x dx. Differentiating u1, we have du1 is 2 dx, and integrating dv1, we get v1 is e to the x. Let me just take this entire integral and do it on the side here. The integral of 2x e to the x dx. Applying the formula for integration by parts, we have uv minus the integral of v times du. Now we can see that we have simplified this greatly. We get the integral of 2e to the x dx, which is a very simple integral. So finally the integral of 2x e to the x dx becomes 2x e to the x minus 2 e to the x. And now plugging this back into our original integral, we get the integral of x squared e to the x is x squared e to the x minus 2x e to the x minus 2 e to the x. Let's not forget plus c. We can actually open this up and factor out an e to the x. So we have x squared minus 2x plus 2 all multiplied by e to the x plus c. Integration by parts also allows us to integrate inverse trigonometric functions. For example, consider integral of arctan x dx. In this situation, it's best to choose the u as the arctan x and the dv as dx. Since u is arctan x, you might remember that the derivative of arctan x is 1 over 1 plus x squared, and so the differential du will be dx over 1 plus x squared. Since dv is just dx, v is going to be x. Applying the formula for integration by parts, we have u times v, which is x times arctan x, minus the integral of v times du, which is the integral of x over 1 plus x squared dx. The integral thus obtained can be found by substitution. We can simply multiply and divide by 2, and we can now set t to be 1 plus x squared, which gives us dt as 2x dx. Performing the substitution, this integral reduces to negative half integral of dt over t. And we all know that the integral of dt over t is just ln of t. So we have minus half natural log of t. But if you remember, t was 1 plus x squared. And so we have minus half times the natural log of 1 plus x squared plus c. Another inverse trigonometric function that you can find is arcsine x. Again, here we proceed by taking u to be arcsine x and dv to be dx. Since u is arcsine x, if you remember, the derivative of arcsine x is 1 over square root of 1 minus x squared, and therefore the differential du will just be dx over square root of 1 minus x squared. Applying the formula for integration by parts, we have x arcsine x minus x dx over square root of 1 minus x squared. And just like the previous example, the second integral can be found by substitution. We can set t to be 1 minus x squared, which gives us dt is negative 2x dx. Just multiplying and dividing by 2, we should get plus half times the integral of dt over square root of t. Now we know that square root of t can be written as t to the negative half, and using the power rule for this integral, we can get t to the half plus c. T was simply 1 minus x squared, and so the final answer should be x arcsine x plus square root of 1 minus x squared plus c. As usual, here are some practice examples for you to get better at integration by parts. The solutions will be revealed in a few seconds.